In this lecture we will make an introduction to electrostatics, and we will start by reviewing the different electric and magnetic quantities that we are dealing with. So we have electric and magnetic quantities, and we have sources as well as fields. The sources are the quantities that create the fields. What are the sources that we have? We are all familiar with the electric charges, so we have electric charges Q, which are measured in coulombs. We have electric charge density ρ, which is measured in coulombs per meter cube. And we also have electric current, or in a more general case, electric current density, J, and that is a vector quantity. And this is measured in amperes per meter squared, and ampere is a coulomb per second, so this is the same as saying a coulomb per second per meter squared. So these are the electric sources that we can meet. We also have electric field quantities, and these are the electric field E, which is electric field intensity, and this is in volts per meter. And we also have D, which is the electric flux density, and this is measured in coulombs per meter squared. In a similar way, we have magnetic sources and magnetic field quantities. A magnetic charge, Q sub m, would be measured in Webers. A magnetic charge density, ρ sub m, would be Weber per meter cube. And we also have the magnetic current density, M. And let's leave this unit empty for now. We have magnetic field quantities, and that is the magnetic field H, which is measured in amperes per meter, and H is the magnetic field intensity. And we also have magnetic flux density, B, and this is measured in Webers per meter squared. So let's look at the units. The electric field intensity, E, is measured in volts per meter. The magnetic field intensity, H, is measured in amperes per meter. The electric current density, however, is not measured in volts per meter squared, but is measured in amperes per meter squared. So, in a similar manner, one would expect from symmetry for the units of the magnetic current density to be related to the electric field, and that is actually the case. So the units for magnetic current density are volts per meter squared, and a volt is a Weber per second, so the units here are Weber per second per meter squared. I should highlight here that Q and Q sub m are the point charges, ρ and ρ sub m are charge densities, and J and M are the current densities. So now that we have defined the fields and the sources, we can take a look at the units and try to understand what Maxwell's equations tell us. And Maxwell's equations is a set of equations that is always true. And there are four equations. The first two, we will talk about them later. Now we will see the equation number 3, which is the curl of the electric field. And this is equal to minus m minus the time derivative of the magnetic field, theta b over theta t. The curl of E, if you remember from the previous lectures, is related to the first derivative of the different components of the electric field in space. So when I differentiate volts per meter in space, I take a spatial derivative, the units will become volts per meter squared. The volts per meter squared are the units of m. the magnetic current density. So the spatial change of the electric field creates, in quotes, magnetic current density. The time derivative of the magnetic flux density, theta b over theta t, would have units of the derivative of b, which is Weber per meter squared, per second. And these are the units of the magnetic current density here, Weber per meter squared per second. So the units of the curl of E, the magnetic current density, and the time derivative of the magnetic flux density are the same. The second equation that we will see, which is also known as the fourth equation of Maxwell, says that the curl of H is equal to J plus theta D over theta T, the time derivative of electric flux density. And again, we will look at the units. The units of the magnetic field are amperes per meter, and the time derivative of amperes per meter would give us amperes per meter squared. The units of current density are amperes per meter squared, and the units of theta d over theta t are coulomb per meter squared per second, and the coulomb per second is an amp. So we also have amperes per meter squared. So this equation tells us that the rotation of the magnetic field in space is related to an electric current and the displacement current, which is what theta d over theta t stands for. So the time derivative of the electric flux density is actually a current. These two equations are the curl equations of Maxwell. The third equation we will see is also known as the first equation of Maxwell and relates to the divergence of the electric flux density D. The third equation, which is the divergence of D, is equal to rho, the electric charge density. When we talk about divergence, we talk about a spatial derivative again of a first order. So the divergence of D will have units of coulombs per meter squared per meter, and the units of the electric charge density are coulombs per meter cube. The fourth equation that we will see, which is also known as the second equation of Maxwell, says that the divergence of B, of the magnetic flux density, is equal to rho sub m, a magnetic charge density. And the divergence of magnetic flux density has units of Weber per meter squared per meter, and these have to be the units of the magnetic charge density, Weber per meter cube. So taking electric charges Q and moving them forms an electric charge density, J. Taking magnetic charges Q sub m and moving them would form a magnetic charge density. However, it is important to note that magnetic charges and magnetic charge densities have never been observed. We use them as mathematical tools and mathematical quantities only to help us simplify or solve problems. In physical cases, and since magnetic charges have never been observed, there is no magnetic charge densities. Therefore, we can set the second equation of Maxwell equal to 0. This also means that the magnetic field lines have to always close on themselves and there are no magnetic monopoles in existence. A lot of people have spent many years to try to find magnetic charges, including famous people such as Dirac, the mathematician. However, no successful effort has been documented so far. The electric field quantities E and T are related with each other through what is called constitutive relations. The first one says that the electric flux density is equal to the dielectric permittivity of the medium in which we are considering the electric field to exist times the electric field intensity, while for the magnetic fields, the magnetic flux density is equal to the magnetic permeability of the medium, mu, times the magnetic field intensity H. The dielectric permittivity has units of farads per meter, and it relates to the capacitance, or how much electrical energy the medium can store, while the magnetic permeability mu has units of Henry per meter. These are Henrys, not magnetic field, and it is related to the inductance, or how much magnetic energy can be stored in the medium. These relationships hold for linear isotropic materials that are called simple materials. So we can now understand that if we know the information about the medium, that an electric field exists or a magnetic field exists inside, then we know epsilon and mu. Then if we know the electric field intensity, we actually know the electric flux density as well, and vice versa. So the electric field quantities can be simplified into 1, and the electric sources can be simplified also into 1. The charges that can be statutary or moving. So now we have understood a few more things about these 4 equations. One more thing to note is that if we look at the equations, the curl equations in particular, the curl of the electric field relates to a magnetic field quantity, theta b, and we know that b is equal to mu times h. So essentially the curl of an electric field quantity, of the electric field intensity, relates to the time derivative of the magnetic field intensity. So it relates to a change in time of the magnetic field. Similarly, the spatial derivative, the curl of the magnetic field intensity, relates to a time derivative of the electric field intensity, because D is equal to epsilon times electric field intensity. So the first equation, the curl of phi, relates the electric field with the magnetic field, and the second equation, the curl of H, relates the magnetic field to the electric field. Because of that, these equations are called coupled equations. The electric and the magnetic fields are coupled to each other, and we can see later that this also means that there is propagation. It is important to remember that the magnetic charge density is always 0, as well as the magnetic current density is also 0. So this term is 0, this term is 0, and if we want to consider static conditions, which means conditions where the electric and the magnetic field are not changing in time, then the time derivative of the magnetic flux density will be equal to 0, and the time derivative of the electric flux density will be equal to 0 as well. In this case, the equations transform into what we see on the right hand side. And here we can observe that the first 2 equations relate to electrostatics, and there is not a single magnetic charge or magnetic field quantity involved. And the second set of equations relates to the magnetostatics, and it does not have a single electric charge or electric field quantity involved. So these equations have now been decoupled under static conditions, because the electric fields are separated by the magnetic fields. Essentially what this means is that we will not be able to generate an electric field from a magnetic field in static conditions. And this means that, you will see later, that this means that there will be no propagation. Let us see some examples of electromagnetics. Electromagnetics is used everywhere. It's astronomy, global positioning system, GPS, motors use electromagnetics, and especially magnetism, LCD screens, plasma propulsion, radars. In fact, in our lab we have developed a radar to measure vital sign signals like the heartbeat and the respiration rate of patients remotely without the use of any wearable sensor or electronic device. Optical fiber is part of electromagnetics. Light is an electromagnetic wave. Cell phones, electromagnetic sensors, telecommunications, microwave ablation for cancer treatment. All these applications would not be possible today if we did not have electromagnetism. You may have seen some pictures like this, static electricity demonstration from a Van der Graaf generator. If you want to see more examples like this, feel free to watch the videos on the links here, and think before you watch them if a person can touch 200,000 volts or not. And we also have electromagnets and Tesla coils that can be used for nice demonstrations, such as the one that you see here that creates some nice sparks in the air. It has been said by Max Halderbrand that electromagnetics has done more than just help science. Since we have such advanced communications, our understanding of other nations and nationalities has increased exponentially. This understanding has led and will lead the governments of the world to work towards global peace. The more knowledge we have about different cultures, the less foreign these cultures will seem. A global kinship will result, and then the byproduct will be harmony. Understanding is the first step, and communication is the means. Electromagnetics holds the key to this communication, and therefore is an important subject for not only science, but also for the sake of humanity. Later in our studies, we will see that we will understand that this course forms the basis for many subsequent modules: transformers, machines, motors and generators, transmission lines, fields, waves, radar, wireless communication, electromagnetic interference and compatibility, this is EMI, EMC, microwaves and antennas. A lot of these subjects are being very sought after by modern industries, including some local ones as well as many global ones in many different countries, and many of you will find jobs and will enjoy careers for many years dealing with electricity, magnetism and electromagnetics. Bodies of stationary and isolated electric charges produce electric fields between them, but not magnetic fields. A current-carrying conductor will produce a magnetic field around itself, but no average electric field. A time-varying electric current will produce both magnetic and electric fields, and this is known as an electromagnetic field. The first table here talks about the fundamental units in the SI system. For length we have meters, for mass we have kilograms, for time we have seconds, for electric current we have amperes, for temperature we have Kelvin, and for the amount of substance we have mole. Remember also the conventional engineering units that we use through prefixes. For example, 10 to the power of 3 is kilo, 10 to the power of 6 is mega, 10 to the power of 9 is giga, 10 to the power of 12 is tera, to the power of 15 is peta, and to the power of 18 is exa. For 10 to the minus 3 is milli, 10 to the minus 6 is micro, with the Greek mu, 10 to the minus 9 is nano, 10 to the minus 12 is pico, 10 to the minus 15 is femto, and 10 to the minus 18 is atto. So we have, in mechanics, we have three basic quantities: length, mass and time. Commonly derived quantities from these three are velocity, for example, which is length over time, meters per second, acceleration, which is length over time squared, or meters per second squared, and force. Does anybody remember the units of force? Force is measured in newtons. But what is a newton? Well, as you remember, F is equal to m times A. Mass, which is in kilograms, times meter per second squared. So kilograms times meter per second squared is a newton. Engineers, like electrical and mechanical engineers, are interested in energy and power. Energy is the force times the distance, that is newtons times meters, or kilograms times meters squared over seconds squared. This is energy, this is work. and it is measured in joules. Power is the rate of change of energy with respect to time, so it's energy over time. So it's energy, kilograms meter squared over second squared, over time. So it's kilograms times meter squared over second cube. And this is power, and it is measured in watts.